Yeah, great, thanks. So I realized I've been a little bit sketchy on the history of the ideas that I've been presenting, so I just wanted to mention briefly some of where the ideas come from. Around the 2000s, motivated by ideas in mirror symmetry and mathematical physics, a special case of the equations that I've been writing down arose, which is the deformed Hermitian-Yang-Mills equation. So the names relevant are Lung, Yao, Zaslow, who obtained it as the mirror under SYZ mirror symmetry of the special Lagrangian equation. And then also Mourinho, Manassian, Moore, and Strominger, who are really string theorists, they also derived it from string theory. There's an analytic theory for line bundles. The situation for vector bundles is much more open, but for line bundles, this equation is already interesting. The names maybe are Jacob, Yao, Collins, and Gao Chen, but there are many others as well. Roughly speaking, the motivating conjecture of them was that the existence of a deformed Hermitian-Yang-Mills connection should be equivalent to stability, but for an object in the derived category of coherent sheaves, but with respect to a special choice of central charge, so this choice here. So I'll change omega to alpha. Alpha is a Kähler class. So there is then a general question, I think it's a kind of folklore question, but advertised and pushed forward by Haydn, Katsarkov, Kontsevich, and Pandit, which is how do we do general Hitchin-Kobayashi correspondences for Bridgeland stability conditions on triangulated categories? So how would we do something quite general, kind of extending this kind of natural question? So really what I've been trying to do is to try to answer this sort of question, but just for the special case of the derived category of coherent sheaves. So the point was, for more general stability conditions, the input is this kind of object, topological choice, central charge that looks not only like this, but more generally like this. They're not actually that different. But the way that we produced a PDE then was just by taking Chern-Weil representatives of all of the individual constituent components. And then we wrote down this equation here. And I think just to give you a flavor of what this kind of equation looks like, it's good to examine what happens for the deformed Hermitian-Yang-Mills equation. So here we start off with this, I guess, kind of natural choice, which is important in string theory, and you get this equation. So note that this is nonlinear in the curvature of the Hermitian metric. I guess that's the big novelty for people who are Hermite-Einstein people. I specifically don't have an imaginary, like a multiplication by I here. So this is real and this is purely imaginary. And so that's why I have to take this imaginary part at the end. The reason is then aesthetically, the stability condition looks like Bridgeland stability conditions. And the fact that you have complex stuff in the theory of Bridgeland stability conditions is actually very important there. The only other thing I want to say is why is this called the deformed Hermitian-Yang-Mills equation? So if you scale omega to k omega, so you're taking the volume of the manifold to be much bigger as k tends to infinity, then you can just kind of formally expand this equation as k tends to infinity, and you'll see that the leading order term is the Hermite-Einstein equation, or at least the weak. I think it's the genuine Hermite-Einstein equation in this case. In general, for these Z-critical equations, you get the weak Hermite-Einstein equation, which is equivalent anyway. So that's the sense in which these are all deformations of the Hermite-Einstein equation in this large volume regime. Okay, so what we were leading up to yesterday was trying to derive these equations through moment map formalisms using a new, as far as I know, a new approach to deriving moment maps, which is more geometric. So I was using the theory of equivariant differential geometry. So I'll also kind of very quickly recap that an equivariant differential form was something of the form takes, I'll try not to write in the dead zone for the video, beta takes an element of the Lie algebra and gives you back a sum of differential forms in a k-equivariant manner. The equivariant differential of an equivariant differential form is just, we do the two possible things to produce a new differential equivariant differential form. So it's defined like this. Equivariantly closed, of course, then means dx is 0. So if we then had k acting on holomorphic vector bundle over a complex manifold in such a way that the Hermitian metric was actually preserved by the k action. So we had a notion of a moment map, mu, which sent k now to, sent x to k joule, a section of k joule tensor nd satisfying the usual moment map conditions, so the pairing of mu with v. If I take the differential, now this is a section of ND, so I need to use the connection to give a one form with values in ND. I asked that this was minus the interior contraction of the curvature of the metric, and this led to equivariant Chern-Bay representatives. So equivariant Chern-Bay representative of v with respect to h was just 1 over j factorial I over 2 pi times curvature plus moment map. Oh yeah, and this needs to take an element of Lie algebra, and I pair mu with v. Okay, so this is just equivariant Chern-Bay theory. So this is more on yesterday. So the only two properties of equivariant differential geometry that I really mentioned, and the only things that I'll use, are two properties, namely preservation under wedge products and preservation under equivariant fiber integrals. So we consider a completely general. I'll explain how the setup that I'm going to give extends or can be phrased in such a way that it looks more similar to the Atiyah-Bott way of thinking about things, which is probably the way that you're all familiar with. So we consider a general equivariant family of vector bundles over X. So curly E over X times B endowed with a Hermitian metric. So I think of this, so X is compact. And I think about this as a family of bundles over X parameterized by B. So B, so these are bundles on X parameterized by B. So for every point B and B, we get a bundle. That's all I'm saying. Okay. So we get a moment map. As I mentioned, when we have a lift of the action to the vector bundle, we actually canonically get a choice of moment map for the vector bundle. So we get a moment map. Mu, where does this go? Now this goes from X times B to section of joule of Lie algebra tensor endomorphism bundle. Okay, so now I can state the theorem, which is joint work with Michael Hallam. Okay, so the claim is that for every choice of Z, we can produce the Z critical equation as a moment map in this general situation. So for each Z, there is a omega B, an omega B, omega Z on B such that the moment map, say sigma Z, so where should this go? This is just a standard moment map, so this should go from B to joule of Lie algebra. Okay, so what is it? It's really the Z critical equation in such a way that it makes sense to phrase it as a moment map. So we pair sigma Z with element of Lie algebra, evaluated at a point B, and I should give you back a number. That's what I need to do. So the number is the integral over X of the trace of pairing of moment map for the bundle E of the imaginary part of e to the I minus phi, and so it's really just the Z critical equation, but evaluated on the bundle over the point B. So this is curly EB, HB, and I hope the notation is clear that this is just the restriction of the bundle to X times point B with the induced Hermitian metric. Okay, and so this is the trace pairing because this is a section of ND and this is an NN form with values in ND, and so we can multiply them. We get an NN form with values in ND. Take the trace, we get an NN form. That's something we can integrate to get a number. Okay, so how do we prove this? So the point is that somehow all we need to do is consider just these basic ingredients of equivariant differential geometry. So associated to a term in the central charge of the form CHJ of E dot alpha to the L dot theta n minus L minus J. We consider, so what do we want to do? So what we're trying to do is construct a, first of all, form omega z such that plausibly we can prove a moment map property. How we do that is by constructing an n+1 form on x times b and taking a fiber integral down to x. So we consider, basically we do this by increasing the number of Chern character representatives, increase the Chern character degree by 1. So we consider 1 over j plus 1 factorial. Let me make sure I get this right. I over 2 pi fh to the j plus 1, so we've increased that degree by 1, wedge omega to the L, wedge theta n minus, this is a capital theta, L minus j. So what is this? This is a complex valued n+1 form on x times b. Okay, so we add these up. So omega z is the fiber integral x times b over b of the following thing, imaginary part of trace e to the I minus y, or sum for j, L of exactly these constituent parts. So 1 over j plus 1 factorial, I over 2 pi, fh to the j plus 1, wedge omega L, wedge theta n minus j minus L. And so the point is that because we've taken a fiber integral and x has dimension n, this is exactly a 1-1 form on B. Yeah, so we've got something. What have we got? Well, this is obviously a closed form. So this thing is a closed form just because you take the fiber integral of a closed form. That's one of the properties of genuine differential geometry, rather than equivariant moment map, equivariant differential geometry. So to prove the moment map equation, it's actually kind of trivial. We just extend this idea to the equivariant category. So to prove the moment map property, so we consider the equivariant analog of this construction. So we consider omega x z to be just exactly the same thing, sum over JL. But now we take, maybe this is the wrong notation. Let me just write down what it is that we'll consider. Imaginary part, e to the minus I phi, 1 over j plus 1 factorial. So we do the same thing, we just replace the curvature by the equivariant curvature. So trace I over 2 pi, fh now plus mu star, i.e. the thing that takes v and gives you the pairing of mu with v, the co-moment map, j plus 1, wedge omega to the L, wedge theta n minus j minus L. So this is an equivariantly closed form on x times b, because I told you that wedges of equivariantly closed forms are equivariantly closed, and this is closed, equivariantly closed by equivariant Chern theory. Okay, so what does that tell us? That tells us that the integral x times b over b of this thing is also equivariantly closed. So just to save a little bit of time, I'm going to just write it down directly. The integral of x times b over b of this thing, this is equivariantly closed on b because x times b over b is an equivariant submersion, because that equivariant family. But this is an equivariant family of bundles over x, which means that the k action is only non-trivial on b. So this section is trivial on x. That's essentially built into the definition of what it means to be an equivariant family of vector bundles. Yep. There is an omega z such that this is a moment map, but that has to be a moment map with respect to something. And that something is b omega z. Yep. Thanks. Yeah, that's it. Yeah, so when we define moment map, we have to be talking about something it's a moment map with respect to. Yeah. There's a caveat that I'll mention at the end about positivity of these things, but yeah. Okay, so this thing is equivariantly closed on B But this is exactly the moment map property. Basically, this thing is an n+1 form with value here. And I need to take a trace. Yep, good. This thing is an n+1 form. So when we take its fiber integral, sorry, this is an n+1 form in the form component. But then if you take one copy of this thing, then we're going to drop down to an nn form. And in particular, when we evaluate this, there are only two possible terms. Like regardless of the powers that we take here of j, there are only two possible terms. So this will equal to omega z plus an equivariant differential form, which I'm going to just kind of write as the thing that sends b and v to integral over x trace of, and it's exactly just the moment map term. Okay, so what's the point? Yeah, so here, because we've got a j+1, in principle, we have lots of terms here of the form powers of f and powers of mu. But in total, this is an n+1 form. And we're taking a fiber integral at most, and we're taking a fiber integral where the fiber dimension is n. So the only things that can happen is we get a form part that's a 1,1 form on the base, or we have one power of mu, and that means we have an nn form along with this mu. That gives us exactly this term. That's really a function on the base for every v because we take fiber integral of nn form and the fiber dimension is n. And then for any other terms, we won't have enough degree components to actually integrate over the fiber. We'll have like, for example, an n-1 form on the fibers. We take the fiber integral, that's just 0. Okay, so to say that this thing is equivariantly closed is exactly the moment map property. So we've just got the moment map property automatically. So this might seem a little bit like magic. And yeah, maybe I agree with you. So I'm going to make a few remarks. So first of all, yeah, maybe the setting is a little bit unfamiliar to people, but I'm going to just phrase it in such a way. So to recover, so first remark, so to recover the ICTS-TIFR result. So what they do is they consider the space of unitary connections in a fixed complex Hermitian vector bundle. So here, EH is just complex Hermitian. So that has a universal bundle over it. So if I take the product with X, then there's a bundle over this thing where it's just, as a smoother complex vector bundle, it's just a pullback of this bundle from X. But this thing actually has a universal connection. There's a natural connection on the universal bundle over the space of unitary connections. The gauge group that we know and love acts on the space of unitary connections. That gives you a trivial action on X and hence on the product of X times this. This actually lifts to the universal bundle in such a way that the connection is actually an invariant connection. So we precisely find ourselves in this situation that we've got an equivariant family of bundles. And exactly this proof works again. And there's nothing different in finite or infinite dimensions here. But the point is that in contrast to the classical ICTS-TIFR picture, which is a direct calculation, I guess, which seems somewhat magical, here it seems to me at least a little bit more principled, that you get moment map property in a kind of canonical way where you make a choice and you get as output a geometric PD. So the same technique applies. So one of the things that I should mention is that integrability is not true in general for this, the fiber-wise bundles here, but integrability isn't actually important in the technique. So, okay, the other thing is that the form that you get, the analog of the ICTS-TIFR from this perspective is the same Taylor metric on this space of unitary connections. The way that works is that really what we're seeing is the kind of more like a Weil-Petersen fiber integral type expression for the ICTS-TIFR Taylor metric rather than the L2 inner product one. And that leads to maybe a quite important comment, which is that omega z is not Taylor in general. So it's a closed 1-1 form, but it's not Kähler in general. This is already the case for the deformed Hermitian-Yang-Mills equation, and something happens on the mirror side also that's the same for the special Lagrangian equation. What I'll just mention is that the positivity is at least explicit and is definitely important. It leads to all sorts of interesting analytic phenomena. Like for these equations, you see obstructions not just coming from, say, torsion-free subsheaves or reflexive subsheaves, but actually subsheaves supported on subvarieties as well, like torsion sheaves. And that seems to come in precisely because of questions around this kind of positivity. So that's maybe an interesting feature rather than a really negative feature. And yeah, so the technique is kind of very general. Somehow the claim in this paper where we explain this, most of the paper is devoted to the scalar curvature picture, which some of you may have heard of, about the Yaotian-Donaldson conjecture, where exactly this idea applies. And we produce kind of very general geometric PDEs in that context as well. But really, the technique is completely the same. Basically, the claim is that if you would like to construct geometric PDEs, what you should have is an equivariant family of objects, a notion of curvature, and a notion of equivariant curvature. Once you have those ingredients, it seems that through this process, you get moment map properties in a very geometric, canonical way. The only choice that you need to make is this kind of form omega z. That comes up from algebraic geometry in also a very principled way. These fiber integrals are analogous to push forwards of determinants or Deligne pairings or words like those. Great, okay, any questions on this part? No? Okay, good. So, how long do I have? Not amazingly loads of time. So I'm going to talk about now Hitchin-Kobayashi correspondence for these equations. Not in general, which is, I think, an important open question, but in the large volume regime. Long title. Okay, so the point is to try to prove that there is a notion of stability that captures existence of solutions of these PDEs, not in complete generality, but just in this kind of large volume regime where we scale the Kähler metric to very large volume. So interested in a vector bundle over xk omega for k very large. So the scales, we fix a vector bundle, we change the Kähler metric by scaling it. Note that the equation is not homogeneous in K in contrast with the Hermite-Einstein theory. So this changes, as in my definition, is we fix an original central charge, but it changes it to what I'll write as ZK. Okay. So definition. So E is asymptotically Z stable if for all F living inside E, so I'm going to be a little bit cautious about saying whether these can be torsion or torsion-free or anything like that. Phi k, if we set phi k should just be the argument of zk of F. Then this argument decreases in subsheaves. So phi k of F is less than phi k of E for k very large. So note this, actually in some sense it looks a lot more like Giesecke stability than slope stability because it's something more akin to a polynomial inequality of numbers, like an inequality of polynomials as opposed to an inequality of numbers. And in fact, everything that I'm going to say, including this moment map technique, works for the geometric PDEs that are related to Giesecke stability due to Lang, these almost Hermite-Einstein equations. That's true of the moment map interpretation, which is originally due to him, and also for this Hitchin-Kobayashi correspondence, which he also has results in the direction of. Okay. Yep. Yeah, okay, so that's a good thing to point out. So omega z, as k tends to infinity, because, I mean, it's the same reason that the equation is kind of converging to the Hermite-Einstein equation, omega z is converging to the Atiyah-Bott Kähler metric. And so that's not uniform across all bundles, but in like a compact, finite dimensional neighborhood of a fixed connection or something, this retains positivity for k very large because of that. Yeah, so the positivity is there as k tends to infinity, and that's of course very helpful in the theorems that I'm going to prove. Yeah, I mentioned this is really totally analogous to what happens in the special Lagrangian equation, where they somehow you should imagine that some kind of positivity of the form should be preserved under a geometric flow, or should be preserved under a natural continuity method or something. Yeah. Yeah.
So maybe you already mentioned this, but I walked in late. But how are you normalizing the angles? Are they in a specific range, or?
Oh yeah, they should be in 0 to 2 pi.
Oh, I see.
Okay, so I also mentioned in normalization yesterday, maybe, that the leading order term in the theta 0, 0 term should be I.
I see.
And if I have the normalization correct, that means for k very large, everything is in the upper half plane.
Right. So is that also related to whether this omega z is positive or not? The range in which theta is selected? If
I don't see that that's the case, but
I see.
Yeah, I mean, I will say that what I'm saying today is roughly the state of the art knowledge in this, especially in this higher rank case. And so most of the questions that you can ask are actually just more like interesting open questions rather than something I can really answer. So yeah, I mean, yeah, that's a good question. But yeah. Any others? Okay, great. So where was I? Okay, so expanding phi k of E minus phi k of F for k very large. So we see that asymptotic Z stability, it implies slope semi-stability just because the leading order term is the difference of slopes. So this implies slope semi-stability. So if we're interested in trying to ask questions of the form, when is it the case that we can find these Z-critical metrics for k very large, then we might as well assume that our bundle is slope semi-stable. So we take, this is again, it's analogous to the relationship between D-square stability and slope stability. So we take a slope semi-stable E over x omega and ask when, okay, it really does not have a Hermite-Einstein metric, but we can ask nevertheless when it admits Z critical, ZK critical metrics for k very large. Okay, this may or may not happen, and you should imagine that it's determined by this asymptotic Z stability, and that's the flavor of the result that we'll prove. So E is slope semi-stable. So that means that it has a polystable degeneration, so it has a graded object. So it has I'm going to do this a bit geometrically. This has a polystable degeneration. So I'm going to think about this as a family of bundles over x times c. This has an S1 or a C star action, which lifts to this universal bundle. This is just like this turning off an extension kind of trick to generate our slope semi-stable bundle to its graded object. So ET for T non-zero is just isomorphic to E, and E0 is slope polystable. It's just the graded object. Note in particular that we have a family of sheaves. This is helpful because of the moment map interpretation I gave, which was specifically designed for families like that. Okay, so we're going to make an additional assumption which is going to be very helpful for the analysis, which is that the graded object is actually a bundle rather than a sheaf. So we assume, so E0, which is polystable, slope polystable, we assume that this is a vector bundle. So it's not singular. Okay. So theorem, which is joint work from 3 or 4 years ago, which is joint work with John McCarthy and Lars Sekman. So the following are equivalent. So it proves a Hitchin-Kobayashi correspondence in this large volume regime. Okay, so 1, E is asymptotically Z. Okay, I'm going to just put in brackets polystable. In fact, let me just erase poly, and I'm going to assume that E is simple. The same holds in the polystable case, but I just, maybe it's easier not to mention it. Okay, and the second is that E admits solutions of these PDEs, so it admits ZK critical metrics for all K very large. And yeah, so somehow we're assuming that E has smooth graded object, and that will mean that this asymptotic Z stability, we'll just check this with respect to F sitting inside E that are actually subbundles. So we'll be able, because of this assumption, to just work with non-singular things. Yep. Okay, good. So any questions on the statement of this theorem? So this is the sense in which I mean that we have some kind of Hitchin-Kobayashi correspondence, but just in this large volume regime. In the paper, we've given some examples of vector bundles that have solutions of these equations for various choices of central charge, but which are not Hermite-Einstein themselves following this theorem. Proof. So 2 implies 1. This follows a general principle in the vector bundle theory. So this follows more classical ideas in the field, namely curvature decreases in subbundles. So the proof is modeled on work of Leung on this relationship between Giesker stability and almost Hermite-Einstein metrics. And so for this part of the proof, we just primarily follow his work. So I just focused on 1 implies 2, which is stability implies existence. Okay, great. So suppose, briefly, okay, so a special case of this theorem, which is not so hard, but which I want to explain, is the case when E is actually slope stable itself. Right? Then it itself has a Hermite-Einstein metric, and stable implies simple, so it has no automorphisms. So we've supposed firstly that E is stable, hence we completely rely on the existing Hitchin-Kobayashi correspondence, hence E admits a Hermite-Einstein metric H. Okay, so it's one of the basic ideas in geometric analysis that once you have a solution of some PDE that's an elliptic PDE, you can perturb the PDE a little bit and retain solvability. So in this situation, we apply the inverse function theorem to construct ZK critical metrics for K very large. So what do you need? One, you need to be, to apply the inverse function theorem, you need a family of operators that are a perturbation of your original one. So the first point is that the imaginary part, v to the minus I, everything depends on k now, of z tilde of e h. So in this quantity, we're scaling the Kähler metric k. This becomes, actually, when we apply the inverse function theorem, it's easier to consider not k going very large, but epsilon becoming very small, where epsilon is 1 over k. So that's easier when we talk about perturbations of things. We like perturbing things just a little bit. So we set epsilon to be 1 over k. And okay, I'm going to put epsilons here instead. So then to leading order, which, if I have it right, this is 2n minus 1, what we get is a constant, c non-zero, times just the Hermite-Einstein equation. Really, it's the weak Hermite-Einstein equation. Plus higher order terms. Okay, so we've got a sequence of PDEs that to leading order up to a not really important constant is the equation that we have a solution for. E is slope stable, so it's Hermite-Einstein. And in particular, I can solve not just the Hermite-Einstein equation, but this one, which is the weak Hermite-Einstein equation. So f is just a smooth function. In particular, the same calculation says that the linearization of the z critical, z epsilon critical operator. So we view this as an operator on Hermitian metrics. So this becomes epsilon to the 2n minus 1 times the same constant times the bundle Laplacian plus O of 2 to the n epsilon to the 2n. So it's the same thing, just we need to say what is the linearization of the Hermite-Einstein operator. It's just the bundle Laplacian. Now the reason I mention this in such detail is that how do we apply the inverse function theorem? What we need to know is something about the kernel of the linearized operator. And the kernel of the vector bundle Laplacian is just the global holomorphic sections of ND. But E is simple, so they're just multiples of the identity. So at least working orthogonal to those multiples of the identity, this is an invertible operator, and so we can apply the inverse function theorem. So it's actually, once you familiarize yourself with this type of analysis, it's kind of a simple result. So I'll write this as p epsilon. Okay, so E is simple. That implies that the kernel of the bundle Laplacian, which is isomorphic to H0 of x nd, this is just the span of the identity element. So in particular, in the Hermite-Einstein equation, we always subtract a constant multiple of the identity. Somehow this persists in the entire theory. And in fact, the fact that the kernel is the identity, we just work orthogonal to that and everything is fine. So inverse function theorem, this applies. So this is the same statement. I mean, you pass to some kind of Banach completion or something, but really it's the same statement as you might have learned in real analysis in several variables. To perturb things, what you need to do is to have control over the linearized operator. So the inverse function theorem applies to give solutions. So the point of explaining this in such detail is really that we see what goes wrong when we drop our assumption that E itself is stable. So what we would like to do is say, okay, well, maybe we don't know that E has a Hermite-Einstein metric, but our assumptions certainly imply that E0 has a Hermite-Einstein metric. So why don't we just perturb the Hermite-Einstein metric to produce solutions of this equation on E itself? The issue is that the bundle E0, that really does have automorphisms, right? That's polystable, not stable. And so this kernel is much bigger. It's the full Lie algebra of automorphisms of E0. So in general, the reason that this result is non-trivial, so the obstruction comes from the kernel of the Laplacian, but now on end of E0, this polystable degeneration. But this has a geometric interpretation. So this is isomorphic to H0 of X and E0. So this is something that comes with algebra geometrically, essentially. So what do we do? So we view this as kind of the obstruction space and say, okay, well, maybe we can solve this equation not equal to 0, but lying in this obstruction space. That's the sort of thing that the implicit function theorem would give you. So, okay, so we can assume that actually we're just changing the connection or Hermitian, connection on a fixed Hermitian vector bundle, first of all. So we can assume that E0 and E have the same complex Hermitian structures, but different holomorphic structures. So they're the same complex Hermitian vector bundle, but with a different complex structure. Holomorphic structure. Then what we do, first of all, is consider the deformation space of curly E0. So our bundle is our bundle of interest E is a deformation of its polystable degeneration. And we would like to consider not just that one, but in fact, all possible deformations on an equal footing to do something a bit more universal. So Kurainishi theory this gives a map from some base B. Actually, it's a bowl in a vector space. To the space of unitary connections on EH. So I view this now as a complex vector bundle. I think it came up in one of the other talks, but this Kurainishi space, it's a deformation space, so it lives inside a vector space, which is just H1 of ND0. So this is a bowl in a vector space. A finite dimensional vector space. Okay, so I'll call this map phi. And this bowl around the origin in a vector space, it has in particular an origin. So phi is 0 is nabla 0, the Chern connection on E0, the graded object with its Hermite-Einstein metric. What I was saying before was that this thing has a universal bundle over it. So if I take products with X, I can pull back the universal bundle to give a family of bundles over the Kurainishi space. And part of this package of Kurainishi theory is two things. So first of all, this is a complete deformation space. So B is so I'll call a versal deformation space. For the graded object E0, which means that any possible small deformation of E0 arises in this family over the base. So in particular, my bundle E that we're interested in lives as one of the fibers here. So E is a fiber over B for some B. And secondly, because this lives, as mentioned in H1 of end E0, there's actually an action of the automorphism group of E0 on the Kurainishi space. So if I take the automorphism group to be the maximal compact rather than the full reductive thing, this B is, it's a bowl in a vector space, so it can't admit like C-star actions, for example. But it does locally. There's some kind of structure theory to that sort of thing. So the second thing I want to point out is that there is a natural action making this a equivariant family of bundles, which again, the point is that this is now really fitting into this moment map perspective I was taking. Okay. So if G is the automorphism group of E0, this is reductive, it's complexification of G, then actually K also acts on X times B over E. So it acts on this universal bundle, but just trivially on X. We're exactly in the setup as before, the same setup as before. Okay. So now we apply the implicit function theorem. More appropriate when we have non-trivial kernels to use the implicit function theorem. So this applies to give new Hermitian metrics that are epsilon dependent, so H epsilon on curly EB, such that the following property holds. Really now, this Z critical operator, it can't be made to be 0 anymore, but at least we can make it to lie in the kernel of the operator that we're perturbing. That has a geometric interpretation now. It's just the Lie algebra of the automorphism group that we have on the whole setup. So we can make it so that the imaginary part, e to the minus I phi, Z tilde of EB, HB epsilon, lives in the kernel of the Laplacian on E0. So we just apply the implicit function theorem, essentially fiber-wise, but we've basically got a smooth family of operators just on the fibers. Okay, so we view this as the obstruction space. This is isomorphic geometrically to the Lie algebra of the automorphism group. Okay. Okay, so what next? Okay, so for my family, curly EB, H epsilon over X times B, we have, as before, a K action upstairs, downstairs, acting trivially on X. So in particular, from the moment map perspective, we know what the moment map is here. So we have a moment map, say, sigma epsilon, such that B goes to dual of Lie algebra of the form sigma epsilon B. At B, I need to give you a number. I give you the number integral over X, trace of mu epsilon B. So these have moment maps in a canonical way. No choices needed. Mu epsilon. Okay, and then we just input the Z critical operator. Okay, so this is the theorem that I proved at the start of the lecture. Okay, so somehow we're almost done. If we had a 0 of the moment map, that would tell us that we live in something that looks a lot like this function space, so space of sections, but it's not exactly. Somehow the fact that they're close enough means that the same argument applies. So what I'll write is that sigma epsilon H does not quite lie in the kernel of the bundle Laplacian because we've perturbed things basically on the graded object with respect to the original Hermitian metric coming from the pullback of the Atiyah-Bott one. But it almost does. And in particular, an idea, so kind of copying an older idea due to Ortu and Seknon. In particular, when you've got these perturbations of operators, what happens is, so a 0 of sigma epsilon is nevertheless a Z epsilon critical metric. So, I mean, imagine that these were literally in this kernel, then we've perturbed, so this lies in the kernel. If this is 0, then that means that its projection onto the kernel vanishes, but if its projection onto the kernel vanishes and it lies in the kernel, then it must be 0. So in particular, for the rest of the few minutes, I'm just going to assume that this already lives in the kernel. So we've reduced our problem to finding a zero of this moment map. Yeah, everything is absolutely epsilon. Thanks. Yep, so for epsilon very small, which is the regime in which one can apply the implicit function theorem. So in particular, we've reduced ourselves to a finite dimensional moment map problem. I'll just mention that, I mean, the natural thing that you might do is perturb at the level of connections rather than perturb at the level of Hermitian metrics. The issue is that if you do that, you're going to kill holomorphicity of the map to the Atiyah-Bott space of unitary connections. So you're going to be able to do the same thing, but you're going to reduce to a moment map problem that's with respect to a non-Kähler symplectic form. If you perturb at the level of Hermitian metrics, you now have varying connection and Hermitian metrics, so you can't apply the older Atiyah-Bott way of thinking about moment maps, but you retain working in Kähler geometry. That's the technical benefit of the moment map interpretation that I gave at the start. If you just tried to use Atiyah-Bott style stuff, you would get stuck because you would land with a problem in non-Kähler symplectic geometry. Okay, so we want to find a zero of the moment map of the moment map sigma epsilon on B. But what's the problem? Really, you might say, well, why don't we just apply the Kempf-Ness theorem? The issue is that B is non-compact. So we're kind of in trouble. So we need to prove some new results in the direction of the Kempf-Ness theorem. So it's non-compact, but I mean, somehow at least it's finite dimensional. So it really is similar to the Kempf-Ness theorem. And the benefit of the story to try to just directly apply Kempf-Ness, so we're at least in a finite dimensional situation. Okay, so what do? We use the gradient flow approach. Which I think was in lecture 1. So we show three things that will allow us to show that the gradient flow approach to the Kempf-Ness theorem actually applies in this situation, regardless of compactness. So first of all, the flow starting in maybe a smaller ball in B remains for all time in B. Basically, for experts, I guess, the point is that the unique fixed point of the G action is the origin. That's what's saving us there, which is a consequence of the setup of Korenishi theory. Okay. So at least morally, we should be able to apply Kempf-Ness. Part 2, what I said is that gradient flow, this flow argument approach to proving Kempf-Ness, either it produces a zero of the moment map or it produces a destabilizing one parameter subgroup. That one parameter subgroup does not have limit, which is the limit point of the flow. That's one of the real subtleties of the flow approach. So if rho from C star into G is the one parameter subgroup generated by the flow, like kind of asymptotic to the flow at infinity, if no zero of mu epsilon or sigma epsilon exists. So I'll say as well, it's really a story that works for fixed epsilon. We're not changing epsilon in this argument anymore. Okay, so if this is so, then for B in B with EB over X isomorphic to the bundle that we actually care about, E, then maybe after replacing B by some other point closer to the origin, the limit as t tends to 0 of rho of t dot B, which is some B0, this also lives in B. So what's this saying? The first part is really saying if the flow converges to a zero at the moment map, then we're fine. It lives in B, and B is where we have control of the analysis, so everything works. On the other hand, if the flow does not converge in the orbit, then the one parameter subgroup that we generate still lives in B. Everything relevant is happening in B. So the third point is that asymptotic Z stability actually gives us control of the GIT weight with respect to this finite dimensional problem. So asymptotic Z stability, this implies that B is GIT stable with respect to these forms omega Z epsilon on B for epsilon very small. So in particular, 1, 2, C, 3. So B cannot happen. We must be converging in the orbit, so we must be finding solutions. So we obtain from stability solutions of the Z epsilon critical equation for epsilon very small, which is what we wanted to do. So this is how you prove this Hitchin-Kobayashi correspondence. That's the end of the course. One thing I just want to emphasize is that, okay, so we prove stability is equivalent to existence in this large volume regime. Somehow the whole point of this theory is that we would like to say something like, in general, solvability of some geometric PDE like these is equivalent to stability in the sense of Bridgeland. That's kind of the guiding conjecture of the whole theory. And this is maybe the first example that shows something plausible in higher rank. This work of the authors I mentioned at the start of the talk in rank 1. So thanks for listening. That's everything.
Yes, please go ahead.
Okay. Yeah. So this notion of asymptotic stability, is that essentially this polynomial stability of Bayer?
Yeah, absolutely, yeah. So he wrote a paper that has some like kind of deep mathematics in it. This is really just a definition modeled on Giesecke stability and modeled on his work. He develops a rich theory of polynomial stability conditions, yeah.
Right, and so can you comment a bit on circling back to like ordinary Bridgeland stability conditions?
Yeah.
Do you have any comments on if you want to use this approach to say go to complexes, because then you lose this entire notion of stability with sub-objects, right? You don't have sub-objects anymore.
Yeah. So there are two different ways that one can try to approach this general question. One approach, which I think is the one that you're working on, is start off with the notion of Bridgeland stability condition and try to work towards maybe an axiomatic notion of what an equation would look like. The other thing you can do is try to start off with some interesting equations and try to work out what the right kind of notion of stability would be. And probably it's not the case that the deformed Hermitian-Yang-Mills is exactly equivalent to Bridgeland stability anyway. So from either perspective, you're going to have to change things a little bit. So the perspective I would take is just to start from the analysis. So what you would like to do is try to generalize this theory to the derived category of coherent sheaves, but just by setting up a PDE theory, first of all, and then second of all, worrying about how you work out the connection with stability. And start off with reasonably explicit geometric PDEs and try to let the analysis guide you as to what the connection with Bridgeland stability conditions is. So I'm kind of, for the moment, less concerned with directly trying to connect it with Bridgeland stability conditions and just trying to develop foundational analytic features that hopefully will show some of these things. Like as I was saying, the positivity of these forms omega Z is related to stability with respect to subbundles supported on subvarieties, for example. So you see kind of more homological elements coming in. I will say that the point of this moment map approach is not that it proves kind of new theorems. I mean, it does, but the framework is completely general. So what I was saying that you need is you need a notion of an equivariant family of objects. You need a notion of equivariant Chern-Bay theory, and you need a notion of a stability condition. Those three things seem to canonically give you geometric PDEs. So if you can do that for complexes of sheaves up to quasi-isomorphism, for example, if you can do that for complexes of vector bundles, which I think it just works basically for complexes of vector bundles, then you get geometric PDEs automatically. Like, so this way of doing things, I think, is the right way of kind of starting off with some kind of category that you're working in and deriving what an interesting geometric PDE is. Yeah.
Maybe just a quick follow-up question to that, which is connected to, I think, what Ved was asking about the restriction on the angle in the PDE.
Yeah.
So do you have any comments on, from the analysis side, if you approach this, what could one try to do? Because when you allow the angle to go beyond 2 pi, then you have.
Yeah, okay. So I think probably Ved is the right person to ask in some sense. I mean, okay, so there's a huge theory of the deformed Hermitian-Yang-Mills equation in rank 1. That's a feature. I mean, Hermite-Einstein is trivial in rank 1. Deformed Hermitian-Yang-Mills is really interesting in rank 1. There, this angle plays a huge role. And in particular, there are various like supercritical phases where we have results that we don't know in general. What I'm working with is not those phases. I'm working kind of close to Hermite-Einstein. So that means that I think the right intuition to have is coming from the deformed Hermitian-Yang-Mills for line bundles story, rather than the analysis I've been developing, which is more transparent in the other regime when you're close to Hermite-Einstein. So I think people would have sensible answers to your questions. I'm not so sure that I have more to say than the deformed Hermitian-Yang-Mills people.
The microphone is here. Do you have problems with Sobolev spaces and stuff like that, or like need to know about the spectral theory of the Laplacian due to the higher the higher terms? They're not higher derivatives, right? They're polynomial terms in the first and second derivatives, right?
Yeah. Okay. So what I'll say is that for this problem, the analysis causes no issues really. So I mean, okay. So to apply the inverse function theorem, I have to pass to some Sobolev completion or Banach completion or whatever. That's completely fine here. In general, one of the big issues with the analysis is going to be, okay, you've got PDEs that are nonlinear in the curvature. I don't know, all of these conditions that work in the Donaldson-Uhlenbeck-Yau theorems, which are like, you've got L2 bounds in the curvature and that gives you some properties. That's going to be really hard to apply here because you've got terms that are nonlinear in the curvature itself. So here everything is fine because I'm a perturbation of Hermite-Einstein. So kind of.
Don't you need to measure the size of the perturbation in some way that
you do, yeah. So you need to measure the size of the perturbation of the linearized operator, for example. But here, what you want is a uniform upper and lower bound, the epsilon, in terms of bundle Laplacian. You get this just from this asymptotic expansion, yep. So that's basically why the analysis that works for the Laplacian, which is kind of completely classical analysis, also applies in this regime where epsilon is small. Outside of epsilon being small, everything looks much harder analytically, but yeah. It's interesting stuff.
So you mentioned you can apply this formalism to the constants to perturb the constant scalar curvature. So the replacement for the universal object there that you know the universal bundle is what exactly?
Yeah, so I am sure this is known to Kuranishi, but we could not find a reference for this. But the space of almost complex structures on a compact symplectic manifold has a universal family over it. Over an almost complex structure, it's just M with that almost complex structure. That has a universal relatively Kähler metric, and the gauge group, which is the exact symplectomorphisms, that lifts to the universal family.
Right, but it's not quite a vector bundle. So that somehow I thought you needed a vector bundle. Or,
you don't even need this complicated notion of a moment map for a vector bundle in that setting. So now you're just applying.
Yeah, so that is, you do have this, indeed, you do have this universal thing.
Yep.
And the group of Hamiltonian symplectomorphism lifts, right?
Yep, exactly. Yeah.
But that's all you need here, right?
That's all you need there. Yeah.
Okay.
So the technical thing that you need to calculate is what are the equivariant Chern-Weil representatives of the Hermitian metric on the tangent bundle that you get from a Kähler metric, say, or really you need the relative version of that. One more advertisement of this idea, one can also derive the Kähler-Yang-Mills equations from this. If you've got here I've got an equivariant family of bundles over X parametrized by B, but if I let B parameterize an equivariant family of bundles over manifolds, you do exactly the same thing and you get the Kähler-Yang-Mills equations.
Thank you.
And suppose that your initial data instead of a holomorphic vector bundle was, say, a pair of a holomorphic vector bundle plus a section, or maybe various holomorphic vector bundles and sections. Does this formalism also extend to that situation?
Yeah, so that's a really interesting question. And I think lots of the features do. And I guess it's an open problem to try to understand those things, yeah. I mean, I don't want to say obviously yes, because I think it would be like a nice thing to work on that seems likely to succeed. But there are things to check and things to do, yeah.
If not, that let's thank Rui for this wonderful lecture series again.